So next up, as Bailey alluded to, actually did a great job of chairing the session for me, I don't really have anything else to do, is Pranav Jain, and he's going to talk about neural Monte Carlo fluid simulation, and this is work with his collaborators at USC, UPenn, and MIT. So Pranav, when you're ready, take us away.
Thank you for the introduction. Hello everyone. Today I'll be talking about a paper, Neural Monte Carlo Fluid Simulation, where I'll cover how one could use a marriage of neural nets and Monte Carlo methods to simulate complex fluid phenomena. But before diving deep, let's quickly understand what the Navier-Stokes equation is. It's a differential equation that governs all fluid flows, and it depends on the velocity and pressure at each point inside the domain. We are going to consider the special case of incompressibility, which means that the density remains constant everywhere. This is what the equation looks like, where U is the velocity, P is the pressure, and G is any external force if applied. Note that the incompressibility condition is handled by the constraint. Now, let's take a look at the velocity a little more closely. Note that it depends on space and time. So if we want to discretize it, we have to discretize it in both space and time. To discretize in time, one of the most popular methods was introduced by Chorin et al. The idea is to solve the Navier-Stokes equation in 3 steps. The first step is the advection step, where we compute U advec. The second step is the pressure projection step, where we use U advec to compute the pressure. And the third and final step is the correction step, where we use both U advec and pressure to compute the final velocity. And then this newly computed velocity can be used to compute the velocity at the next time step by repeating the 3 steps again. Note that the incompressibility condition is handled by the velocity correction step. So now that we know how to discretize in time, one of the key challenges that we try to tackle in our work is how to discretize it in space. One of the most common ways is to use a grid. Given a point on the grid, we can use some function to get the final velocity. But what if the point doesn't lie on the grid, but lies somewhere in the middle? What do we do then? Some might argue to use techniques like interpolation, or maybe some other schemes. But unfortunately, they all lead to even more approximations. Therefore, to minimize approximations, we need mesh or grid-free methods. That is, given a domain, choose any point x and evaluate some function to get the final velocity without relying on any mesh or grid discretization. So now that we know why mesh or grid-free methods are important, the key question is how to compute this function we are talking about. Well, why not use neural nets? Because they are inherently smooth, can be queried anywhere, and are cheap to query once trained. One of the previous methods, called INSR in short, tried this technique. They used neural networks for all the 3 steps we talked about earlier. Basically, given a domain, they chose a point x, feed it into the neural network, and the neural network spits out the velocity or pressure depending on which step is being solved. The method works well, but fails when obstacles are involved. This is a comparison with a grid-based method for the von Karman flow. Note that the flow is very noisy, and we notice some boundary artifacts as time passes. Looking at this result, our first speculation is that boundary constraints aren't handled properly. And our second speculation is that neural networks can't solve the pressure projection step accurately. So now that we have a list of speculations, let's try to solve them one by one. Let's start with the boundary constraint issues. Note that we are trying to discretize velocity, and at the boundary, we don't want our fluid to escape, and hence want its velocity to be 0. INSR adds an additional term to the loss function, and we suspect that is the reason for the artifacts, since it doesn't guarantee that the boundary constraints are always fulfilled. So how do we ensure hard boundary? Consider a fluid flow around an obstacle with the constraint that the velocity must be 0 on the surface of the obstacle. Consider 2 points, x1 and x2, outside and on the obstacle respectively. Since we have some fluid flow, the velocity at x1 must be non-zero, but because of our constraint, the velocity at x2 must be 0. Note that we have to be careful not to introduce discontinuity by naively setting the velocity at x2 to be 0. So how do we ensure continuity? Consider a velocity vector u around a boundary shown in blue. We want the velocity to remain unchanged outside an epsilon distance from the boundary. But once it is within an epsilon distance, we want it to gradually go to 0. And once it touches the boundary, we want it to be exactly 0. To get this behavior, we use cutoff functions. In our work, we use the linear cutoff function because of its simplicity. The function value is exactly 1 outside an epsilon distance and linearly goes to 0 within an epsilon distance. So if we multiply the velocity with the cutoff function, we can ensure smooth, hard boundary constraint. Note that it's a little more involved than this, since tangents and normals are treated differently. Refer to our paper for more details. Also note that this technique has been employed by previous works, for example, by Liu et al. So to ensure hard boundary, the method is as follows. Given a domain, choose any point x, feed it into the neural network, get the output, multiply the cutoff function to the output, and that will be our final velocity. Okay, let's recap our to-do list. We have solved the boundary constraint issue. So let's see how to solve the pressure projection step accurately. The issue with neural networks is that they are bad at solving high-order PDEs because of numerical errors with auto differentiation. So we need something that is, again, grid-free, but can solve higher-order PDEs. So how about we use the Monte Carlo method? Maybe something similar to the work we saw earlier this session. In our work, we use walk on stars, whose follow-up work was just presented before me. Just as a recap, walk on stars is a Monte Carlo method that can be used to solve a Poisson's equation. And in fact, the pressure projection step is a Poisson equation. So our algorithm is as follows. Remember, we are trying to solve the Navier-Stokes equation. So for the first step, we use a neural network similar to INSR, but with hard boundary. For the second step, we use walk on stars, and this is our Monte Carlo step. And for the third step, we again use a neural network similar to INSR, but with hard boundary. Okay, that was a lot of technical stuff. And if you feel sleepy, that is understandable. But you can wake up now, relax, and enjoy the results. This is a real-life experiment of the von-Karman flow. Notice the vortices being formed in front of the obstacle. This is our simulation result for it. Note that it's still a little noisy, but we do observe the vortices and is a significant improvement from the previous INSR method. This is the smoke rings colliding experiment. Note that our method results in a ring forming, and we even get the dumbbell-shaped structure in the middle. But our method is not able to capture the much finer details like the vortices on the ring. This is an example of a fluid interacting with an obstacle. Note that the fluid doesn't pass through the obstacle, showing that the boundary constraints are accurate. Moving on to limitations, unfortunately, our method is not yet at par with grid-based methods, both performance and accuracy-wise, as can be seen in this example. Our method fails to preserve symmetry. For the smoke plume rising experiment, we observed this cave-shaped structure in the middle, but should have observed a somewhat symmetrical result. Finally, parameter tuning is important to get decent results. For the smoke rings colliding experiment, if we use 2 layers in our neural network, we don't get the ring, but do observe it with more layers. Note that this is a limitation to all neural network-based algorithms and is not inherent to our work specifically. Next, we thought of some open questions inspired from our work. So Monte Carlo methods usually result in a noisy output. So the question is, can we train a stochastic gradient descent-based neural network with a noisy Monte Carlo output to improve on the accuracy? And this leads to our next question. This leads to the next question, can we couple neural networks and Monte Carlo methods in a single step to solve multiphysics problems? Finally, we would like to thank the following people without whom this work wouldn't be possible. And to end my presentation with a quote, Leonardo da Vinci said, "Water is the driving force in nature," and we hope that this method would be a driving force for all future grid-free fluid flows. Thank you.